Chapter 4, Section 6, Numerical Integration. Well, we are able to do integration, as I mentioned before, on functions that are set up. We can't integrate anything, just anything. It has to be set up to fit one of our formulas, one of our integration formulas. Well, some elementary functions just don't have antiderivatives or the ability to be integrated, such as the example I have here, the cosine of x over x. So if we wanted to do a definite integral that involved a function like this, the fundamental theorem of calculus wouldn't help us, because if you can't find the antiderivative, you can't apply the theorem. So instead, we use one of two numerical approaches. One is called the Trapezoidal Rule, and the other one is Simpson's Rule. Now, it's the Trapezoidal Rule that we're going to be concerned with, because Simpson's Rule is not part of the AP. It's not that much more difficult, but it is a numerical way of coming up with the value, the definite integral. And of course, because it's a numerical way and because it's going to involve some calculations, in this case with the Trapezoidal Rule of finding area of trapezoids under the curve, then we are going to be just approximating this, but we can come up with some pretty reasonable approximations by using the Trapezoidal Rule. Now, let me move this up just a little bit. The Trapezoidal Rule, what we're going to do is we still have our curve, y equals f of x. We're going from A to B. We have subintervals here. We partition this. We can make these so that it's a regular partition. That's perhaps the easiest way to do it. So I'll call it delta x b minus a over n. And we're going to try to find the area under the curve, which would be the definite integral from a to b of f of x dx. So instead of using inscribed or circumscribed rectangles, now look at the very first one. If I used an inscribed rectangle, look how the area differs from the area under the curve, from x sub 0 to x sub 1. If I used a circumscribed rectangle, look at the difference here again. It's pretty good amount that would be in error. This would be an over approximation, this would be an under approximation. But if instead of using a rectangle, I connect from here to here with a straight line, and I have, since these are vertical here, I have two parallel sides. I'll just kind of outline it in red here. Okay, I have a quadrilateral with one pair of opposite sides being parallel. I have a trapezoid, and I know how to find the area of a trapezoid. What I'm going to do is I'm going to find the area of the trapezoid of each one of these, and I'm going to add them all together. Now, it's a little tedious to go one at a time, but fortunately the Trapezoidal Rule gives us a way to kind of cut through it a little bit easier. Now remember here, look for example this guy. The area of a trapezoid is 1/2 times the height times the sum of the bases. The height is actually going to be this distance here, because it's perpendicular distance between the two bases. So that's going to be my height. Well, that is delta x. That's this part right here. That's delta x. The two bases, that would be this distance here and this distance here, that would be the y values on this curve at x sub 0 and x sub 1. So this is a little bit more general. This is for the ith subinterval, but it would be the y values, f of x sub I and f of x sub I minus 1. Those would give me the two y values. Those would be the bases. And so what I'm going to do here, and hopefully you can see it, although it's really messy, is that I'm going to take 1/2 times the height, that's the delta x, that's b minus a over n, times the sum of the two bases, that's for the first trapezoid, f of x sub 0 and f of x sub 1, plus, then I'm going to do the next one here, so I'll do the next one here in green. Oops. All right. And so, again, the height is this distance in between here. That's delta x, or b minus a over n. So 1/2 times the height times the sum of the bases at x sub 1 and x sub 2. The left endpoint, the right endpoint. Then I'm going to add it to the next one. I'll go back to red here. That would look like this. That trapezoid. So that's 1/2 times the height times the sum of those two bases at the left endpoint and at the right endpoint, the bases being the y values. And I continue this process all the way down to the very last guy, which would be this trapezoid here. Okay, that trapezoid, again, all the way down to here would be 1/2 times the height times the sum of the two bases being at the left endpoint and the right endpoint. Now, that's a mess. Notice the three dots here because this continues, I don't know, and subintervals. I am going to point out, though, that this is common to every one of these areas. I am going to factor that out right here. So if I factor that out, that means it's now, this is gone, this is gone, this is gone, dot, 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 this is gone, this is gone, this is gone. What's left? Well, I have f of x sub 0 plus f of x sub 1. That's this guy. Then here, plus f of x sub 1 plus f of x sub 2. That's the second one. See, I've underlined them. That's the second one. Here's the third one. F of x sub 2 plus f of x sub 3. And I continue this all the way to the end here. Here's the second to last one, f of x sub n minus 2 plus f of x sub n minus 1. And then the last one, f of x sub n minus 1, f of x sub n. And what I notice here is another pattern. I have two of these. I have two of these. I'm going to have two of these if I had the next one. I'm going to continue having two of these, except I only have one of these and I have one of these at A and at B. So one of those, but I have two of these. I have two of these all the way up to two of these, and one of these. So look at the pattern. 1, 2, 2, all the way, 2's all the way through to the last one, which is a 1 for the coefficient. The 1/2 and the b minus a over n, I just wrote as b minus a over 2n. So this guy right here is what gives me the trapezoidal rule theorem. Let f be a continuous function on the closed interval from a to b. The trapezoidal rule for approximating, not getting an exact value, but approximating the area under the curve, or the definite integral from a to b of fx dx, is given by the integral of fx dx as x goes from a to b here, equals b minus a over 2n, that's this part, and then that long sum here where it goes 1, 2, 2, 2, 2, 2, 2, 2, 2, 2, and with a 1 on the end. Now, just like we did with inscribed and circumscribed rectangles, lower sums and upper sums, if we increase the number of subintervals, we get a better and better and better approximation. In fact, as n goes to infinity, this approximation is actually going to be an exact value. So, with that in mind, let's do an example here. We'll do an example when n is 4, and we'll do an example when n is 8. We should get a better value here, a more exact value here, because we have more subintervals. Now what I like to do is I like to draw out a number line here. I'm going to go from negative pi over 2 to pi over 2. And I'm going to have 4 subintervals, so that means I'm going to cut it in half, that'd be 0, and then I'm going to cut the halves in halves. So that'd be negative pi over 4, and that'd be pi over 4 here. So this is equal to, or approximately, from negative pi over 2 to pi over 2, the cosine of x dx is approximately b minus a, there's b, there's a, so pi halves minus negative pi halves, all over 2 times n is 4, times f of the first endpoint here, which is negative pi over 2, plus 2 times f of negative pi over 4, plus 2 times f of 0, plus 2 times f of pi over 4, plus f of pi over 2. So I have a little bit of calculations to do here. So I have pi over 2 minus a negative. That's the same as adding the opposite. So that's just pi over 8. Pi over 8. What's f of pi negative pi over 2? Well, here's my function. My function f of x is the cosine of x. Cosine of x. If I could write it, I'll try it again. That's pretty messy. The cosine of x. There we go. So what's the cosine of negative pi over 2? Well, the cosine of negative pi over 2 is 0, plus 2 times, what's the cosine of negative pi over 4? Well, the cosine of negative pi over 4 is the square root of 2 over 2. So the square root of 2 over 2, plus 2 times, what's f of 0? The cosine of 0 is 1, plus 2 times, what's the cosine of pi over 4? Well, that's the square root of 2 over 2. And what's the cosine of pi over 2? Well, that's 0. So this is kind of nice. These cancel. These cancel. So I have pi over 8. What's that going to be? So I have square root 2, and a 2. So I have 2 square roots of 2 plus 2. Now, let me get Mr. Calculator out, and let's see exactly, or not exactly, but let's see what this is close to. So I have 2 times the square root of 2 plus 2 times pi over 8, and I get this to be 1.896 to 3 decimal places. There we go. Now, let's see what happens if we do this when n is equal to 8. So it's kind of the same approach here, but we're just going to have some more values to plug in here. So again, here's negative pi over 2, here's pi over 2. So I need to split it. That'd be 0. Need to split it again. That'd be negative pi over 4, and that'd be pi over 4. Then I need to split it again here, 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 and here. So that would be 3 pi over 8, pi over 8, negative pi over 8, negative 3 pi over 8. So this is going to be from negative pi over 2 to pi over 2 of the cosine of x dx is approximately, this is going to be pi over 2 minus negative pi over 2 all over 2 times 8 this time, because n is 8, times, now I've got a whole lot more to add here, because I'm going to have the left end point, negative pi over 2, f of negative pi over 2 plus 2 times f of negative 3 pi over 8 plus 2 times f of negative pi over 4 plus, I bet you I can't squeeze this all in, plus 2 times f of negative pi over 8 plus 2 times f of 0 plus, we're not going to use 3 dots, but plus, I just bring it down here, 2 times f of pi over 8 plus 2 times f of pi over 4 plus 2 times f of 3 pi over 8 plus f of pi over 2. Yikes. So again, this is pi. This would be pi over 16. This is going to be here. Now, I already know that this is 0. I don't know this one. But since cosine is an even function, this is going to be the same as this. And this one here is going to be the same as this one here. So I'm not going to have to do it all over for 4 values, but I do have to get Mr. Calculator handy. So first one up, I'm going to have to grab my calculator, and I need to take the cosine of negative 3 pi divided by 8 and this turns out to be 0.382, let's go 7 for right now, plus this one here, we already did that, that's going to be, oh wait a minute, it's 2 times that, doggone it, times 2. Let's try that again, forgot to multiply by 2. So that's going to be 0.7654, and then this one is going to be 2 times the square root of 2 over 2, plus, now I have to do negative pi over 8, so the cosine of negative pi divided by 8, and then I got to double that. Turns out to be 1.8478, that's this guy, plus 2 times, this would be 2 times 1. And then this is the same as this, so that's going to be 1.8478. And then 2 times what I had here before, and I got to bring it down here, square root 2 over 2, plus this is going to be the same as this, that's going to be 0.7654 plus 0. All right, so this guy here, this guy here, this guy here, this guy here all get added up to what I had in here before, because that's what the 0, the 2's cancel here, 2 and the 2's cancel here. So I'm going to take 2 times the square root of 2. I'm so lazy. And I'm going to add 2 to that. And then I'm going to add 2 times this and 2 times this, because there's 2 of them here and here. So that'd be 2 times 0.76554 plus 2 times 1.8478. So now I have pi over 16 times 10.05483. I'm going to round to 3 decimal places when I finally get done with this. So I'm going to now figure out what this mess turns. That's a 16 there. It looks almost like a 10. So I'm going to divide by 16 and multiply by pi. And I get 1.974. Now look at my first approximation. Look at my second approximation, where n was bigger. If I had to take a guess, I would be willing to bet that my answer is probably 2. Let's see. We can actually integrate this, so we can check our work here. The integral from negative pi over 2 to pi over 2 of the cosine of x dx is equal to the sine of x running from pi over 2, or negative pi over 2 to pi over 2. So this is the sine of pi over 2 minus the sine of negative pi over 2. So this is 1 minus a negative 1, and this is 2. See how we get a better approximation? That's the exact value. Okay, but these were better approximations because we increased the number of subintervals there of a regular partition. So the good news is you don't need to know Simpson's rule and have 2 things to memorize. You do need to memorize the trapezoidal rule. They have a tendency to throw those in on occasion on the AP test. So it doesn't hurt to practice, practice, practice. And the good news is we're ready to get into chapter 5 and do some applications of integration. And we're also going to look at how to differentiate and integrate some other kinds of functions, including exponential functions and logarithms. So lots to look forward to, but for right now, lots to practice using numerical integration.